Let's continue to look at acids and bases. In our previous video, we talked about the relative strength of acids and bases and using pKa values. In this video, let's focus on acid-base reactions. Now, Bronsted-Lowry acid-base reactions are proton transfers. Although remember that they are driven by electrons. So I like to think about the base grabs a proton. Now, in this example, we have acetic acid, so CH3, double bond O. The C is also connected to the O, that's connected to the H. Plus water reacts to form acetate ion plus H3O+. So what's happening here? This is acting as that acid, this is acting as the base. The base grabs off this proton, forming H3O+, which is our conjugate acid. And once the base grabs off this proton, we are left with the conjugate base, acetate. So this is our conjugate base. Double check in the reverse direction. This is acting as the base. It's going to grab off a proton from the acid to give us these two products. These are written as equilibrium reactions because the forward reaction will happen and the reverse reaction will happen. When equilibrium is reached, the concentration of these no longer change. Now we can look at a table of pKa values and we would see that acetic acid has a pKa of 4.7 and our conjugate acid, H3O+, this has a pKa of negative 1.7. So this one is our stronger acid with a smaller pKa value, and this one is our weaker acid. Because this is our weaker acid, that means this one is going to be our stronger base. Because this is our stronger acid, that means this is going to be our weaker base. Because this reaction is in equilibrium, we want to think about these reactions as competition between two potential acids and two potential bases. Who gets to act? Right? Because here we have a weak acid and weak base, and they say, we want to react. Here, our strong acid and strong base say, no, 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 we want to react. Well, the stronger acid and stronger base win the competition. This gets to be the acid, this gets to be the base, and then these guys kind of have to settle for, oh, well, I guess I don't get to react. In the grand scheme of things, yes, they are still reacting because it's at equilibrium. But if we think about who gets to do it more, right, then the strong acid, strong base, they get to be the acid and base. And so this stronger base gets to grab off the proton to form the conjugates. Bronsted-Lowry acid-base reactions are equilibrium reactions, and the equilibrium lies toward the weaker acid, weaker base. Because it's a competition between the acids and the bases, the stronger acid, stronger base wins the competition, and so what exists is mostly the weaker acid and weaker base. So for the first reaction we have on this slide, we would draw our equilibrium arrow pointing to the left. And by saying the equilibrium lies to the left, what we're saying is that at equilibrium, we will have a higher concentration of these species and a smaller concentration of these species. Now, let's look at another example. We're using the same acid, acetic acid, only now we're using ammonia as our base. So this is our acid, this is our base. When ammonia grabs off a proton, it forms the conjugate acid ammonium ion. After acetic acid has given up its proton, what we have left is our conjugate base, acetate. Once again, we need our pKa values, and this still has a pKa of 4.7, but now we're looking at ammonium ion, which has a pKa of 9.3. Again, these values are coming from tables. So now 4.7 is smaller than 9.3, which means this one is our stronger acid and this one is our weaker acid. Because this is the weaker acid, that means this one would be the stronger base. Because this is a stronger acid, that means its conjugate would be the weaker base. So in this case, the equilibrium lies to the right. Talking about strong versus weak is really not relevant because what we need to think about is stronger versus weaker. In this example, acetic acid was the weaker acid, but in this example, acetic acid was the stronger acid. So thinking about acetic acid with an absolute classification of being strong or of being weak, it's irrelevant and it can be confusing. Instead, we want to focus on the particular reaction. When this is reacting with a particular base, it happens to be the weaker acid. When acetic acid is reacting with a different base, then it happens to be the stronger acid. So we need to remember that stronger and weaker is all relative. Let's look at a few more examples. This is called methanol. It's an example of an alcohol. And this is sulfuric acid, an acid that you might have talked about in earlier chemistry classes. And what's happening here? Methanol is acting as the base, and it grabs off a proton from sulfuric acid, which is acting as our acid. After methanol grabs the proton, what we have left is protonated methanol. So there are now two hydrogens connected to this oxygen, and the oxygen has a formal charge of +1. This would be our conjugate acid. And then after sulfuric acid has given up its proton, what we have left is HSO4 minus, and so this one is our conjugate base. In our next example, we are again using methanol, but this time we are reacting it with methylamine. We have the nitrogen here, and the nitrogen is going to act as the base. This is going to grab off a proton from methanol, resulting in methoxide, CH3O-, and the methyl ammonium ion. So in this case, this is our base, and this is our acid. This is our conjugate base, and this is our conjugate acid. We can see that this acted as the base because it now has an extra proton. We can see that this was the acid because this grabbed off the proton, leaving CH3O-. In the reverse direction, this acts as the base to grab off one of these protons to form these products. So in this pair of examples, we have the same compound, in one case acting as a base, and in another case acting as an acid. So this is really an extreme case of where it's all relative, because depending on what else is present for something to react with, not only can it be the stronger or the weaker acid, but it can be the acid or it can be the base. So there's a number of compounds that could potentially act as either an acid or as a base. Alcohols, this is one set of examples. Water itself can act as either an acid or a base. Amines could potentially act as an acid, usually a base, but in some cases it could be an acid. And then here we have another example. So this is acetone. It's an example of a ketone where we have a carbonyl, a C double bond O, and then the carbonyl carbon is connected to two other carbons. This is a ketone, and in particular, this one is called acetone. So if acetone reacts with hydroxide, hydroxide can act as the base. It can grab off one of these protons, which puts these electrons onto the carbon. And so what we have then is water plus the conjugate base. We have a negative charge on the carbon. And we can also draw another resonance structure. Let's imagine that these electrons move here and these electrons move here. So that gives us another resonance structure that looks like this, where we have a double bond between the carbon-carbon and a single bond between the carbon-oxygen, and then the negative formal charge is on the oxygen. So this, as an acid, is very different from just a regular alkane, where we just have carbons and hydrogens and just single bonds, because this conjugate base is stabilized by resonance. Next semester, we're going to see some really useful applications of this ion. Now, if we look at this overall, what we see is that this is acting as our acid, this is acting as our base, this is our conjugate acid, and this is our conjugate base. Now, in another example, we are starting with the same starting material, acetone, but now we're reacting it with HCl. HCl, hydrochloric acid, that is an acid. So this is our acid, and this is going to act as our base. So this pair of electrons can be used to grab the proton, putting the shared pair of electrons that I didn't draw in here, the shared pair between the hydrogen and the chlorine, move onto the chlorine. And so that gives us, we still have this lone pair on the oxygen, but the other lone pair has now formed a bond to the hydrogen that used to be part of HCl, and we have Cl minus. So these three lone pairs were originally present, and now there's another lone pair, and there's a negative formal charge on the chlorine and a positive formal charge on the oxygen. Acetone has acted as the base, forming this conjugate acid, and hydrochloric acid acted as the acid, giving us chloride as the conjugate base. So we need to watch out for species such as methanol, such as acetone, that could potentially act as either acids or bases, depending on what they react with. Here we have a few more examples, and we have acetic acid, and notice it's written a little bit differently, CH3CO2H, but we're still talking about C double bond O, and then this C is connected to the O, which is connected to the H. This is an example of a carboxylic acid, specifically acetic acid. This could react with water, for example, or it could react with hydroxide. So if this is acting as our acid and this is our base, then we would imagine that one of the lone pairs on the oxygen acts as the base, grabs off the proton. So that is going to give us CH3COO minus plus, because H2O was the base, it grabbed off another proton, so now we have H3O plus, right? So we started out with OH, H, and two lone pairs. Now we have OH, H, only one lone pair, and a positive formal charge on the oxygen. If we look at our next example, this is again the acid, this is the base. If this base grabs off the proton, then we can get CH3, COO minus, and water. Now up above, we had, so acetic acid was our acid, water was our base. So this is the conjugate base, and H3O plus is the conjugate acid. In the second example, acetic acid was still the acid, so acetate is the conjugate base. Hydroxide was the base, so now water is the conjugate acid. So we can write out our reactions, but let's also think about the position of equilibrium. So with the position of equilibrium, we want to focus on the pKa's of the acids. So we need this pKa value, and we need these pKa values. So as we saw earlier, the pKa of acetic acid is 4.7. And what about water? Okay, so here we have the pKa of water is 15.7. But wait a minute, this is our base. This is our acid. We are using H3O plus is our conjugate acid, so we don't care about the pKa of water. We need the pKa of H3O plus. So the pKa of H3O plus is negative 1.7. So in our first example, we're talking about 4.7 versus negative 1.7. So this is our stronger acid, and therefore the equilibrium lies to the left. So at equilibrium, we're going to have lots of starting material and only a little bit of the acetate ion and H3O+. In our second example, we have acetic acid is our acid, and now we have water as our conjugate acid, right? Here, water was our base, but now water is our conjugate acid because hydroxide was the base. So here we need the pKa of water itself. So the pKa of water is 15.7. So here we're looking at 15.7. So now this one is the stronger acid and this one is the weaker acid. Therefore, equilibrium lies to the right. So when we are working with compounds that could be either acids or bases, we have to be very careful and make sure we are using the correct pKa values because it makes a huge difference in terms of your understanding of what's happening. All right, here we have another example, and we have methanol and acetic acid. Oh, well, okay, we've had acetic acid acting as an acid, but we've had methanol acting as both a base and as an acid. So which way does this go? We have a pKa value for acetic acid, and for protonated acetic acid, we have a pKa value for methanol and for protonated methanol. Well, let's think about this both ways. So I'm just going to rewrite this. And if we're not sure what's happening, let's try it out. So one option is that methanol is the acid and acetic acid is the base. And if that's the case, so here we have this acts as our base. This is going to be the more basic atom. And so this is going to grab off a proton from here. So that would give us CH3O minus and CH3COH plus OH. And this is stabilized by resonance. So we could draw another resonance structure. If you had this acting as the base, then you wouldn't be able to draw another resonance structure. So that's one way that we could tell which of these two is going to be acting as the base. Let's finish classifying our species. Because methanol was the acid, that means methoxide would be the conjugate base, and then because acetic acid was the base, that means the protonated acetic acid would be the conjugate acid. Looking at pKa values, methanol has a pKa of 16, and the protonated acetic acid has a pKa of -8. This is definitely the stronger acid, and so this equilibrium lies very far to the left. All right, let's think about the other possibility where methanol acts as the base and acetic acid acts as the acid. Well, this base would grab off this proton, and so we will get CH3OH with a positive formal charge on the oxygen, and CH3COO minus. Because methanol acted as the base, then protonated methanol is the conjugate acid. Because acetic acid acted as the acid, that would mean that acetate is the conjugate base. So we need to compare this acid with this acid. Acetic acid has a pKa of 4.7, and protonated methanol has a pKa of -2. So we're still talking about this as the stronger acid, and so the equilibrium still lies to the left. But out of these two reactions, it's much more likely that acetic acid is going to be the acid and methanol is going to be the base, even though at equilibrium there's still going to be lots more of this than these. Really, we could think about an even broader equilibrium where some of this exists, some of this exists, and some of this exists. All right, in terms of overall quantities, we have mostly these, we have a smaller amount of these, and then a teeny tiny amount of these. In practice, we can really ignore this, right? But I wanted to go through this example, not to confuse you, and I'm sorry if that did, but just so that you can think about, even if you don't know which one is the acid and which one is the base, you can go ahead and apply the numbers and figure out who is most likely to act as the acid, who's most likely to act as the base, and by thinking about the position of equilibrium, you can determine that if this is what happened, because there's such a big difference in pKa values, this equilibrium would lie so far to the left that we have almost exclusively these and almost none of these. On the other hand, if this is what happened, then because there's still a significant difference, but not as big a difference as what we had here in our pKa values, the equilibrium still lies to the left, but in this case, we're going to have a lot of this and a small but probably measurable amount of these species. And finally, one more set of examples. We have already looked at things like alcohols, carboxylic acids, and ketones, and we talked about, okay, who's the acid? But let's look more closely at these. If we're talking about ethanol, well, we have this hydrogen, which could be acidic, and then we have these hydrogens as well as these hydrogens. We focused on this hydrogen as being acidic, but we could also think about these. Why did we focus here? Well, if we look at a table of pKa values, this hydrogen has a pKa of about 16, and our typical table of pKa values isn't going to give us numbers for these. But the CH3, the CH2, because they are not next to a carbonyl, because they are just connected to carbons, then they're going to be similar to CH4, which is on a table of pKa values, and this has a pKa of about 60. So because they are similar, then we can estimate that these are going to have a pKa of about 60. So these are really weak acids, and this is the stronger acid within this molecule. So if a generic base comes along, it is going to try to grab off the most acidic proton. And in this case, it is this one. So even though we have multiple sets of hydrogens, we focus on the most acidic hydrogen in the molecule. That's where the base is going to react. If we look at our next example, acetic acid, we have this hydrogen and we have this set of hydrogens. We've already seen in a table of pKa values that this hydrogen has a pKa of about 4.7. And this is not going to be given in a table, but notice that here we have a CH3 group next to a carbonyl, just like this CH3 group next to a carbonyl. I mentioned a few slides ago that if this proton was pulled off, then we have our conjugate base with a lone pair here, but that conjugate base is stabilized by resonance into the carbonyl. The same thing would be possible here. So that means that we could estimate the pKa of these hydrogens as being similar to these hydrogens. So that means we're looking at a pKa of around 19. Now, the fact that this also has an oxygen, it's not going to be exactly 19, but that's a ballpark figure that we can use. If we compare this hydrogen to this set of hydrogens, we can see that these are definitely the most acidic hydrogens in this molecule. And so if a base comes along, it's not going to try to pull off these hydrogens. It's going to go for the easiest ones, which would be this one. So a base is going to pull off this proton. So we've already been doing this, is just focusing on the most acidic hydrogen in the molecule, but I wanted to take a step back and acknowledge that, right? Because sometimes you might be faced with molecules that have multiple sets of hydrogens that could be considered relatively acidic, and you have to decide who's going to react. So let's look at a couple of examples. If we have this compound where we have a carboxylic acid and we have an alcohol, and now we have a base. So the base can either grab off this proton, or it could grab off this proton, or it could grab off any of these. So let's think about pKa values. Because this is a carboxylic acid, then it's going to be similar to other carboxylic acids. And so this is going to have a pKa of, let's say, around 5. This one is an alcohol. So this is going to be similar to other alcohols. So this will have a pKa of probably around 17. This one is next to a carbonyl, so it might be kind of like this. And so maybe this one has a pKa of around 20, 19, 20, probably higher than that. But and then this CH2 group, it's not right next to the carbon of the carbonyl. So maybe this one is going to be more like these. And so this one might be closer to 60. So these numbers might be really off in terms of an estimate, but who cares? Because they're so much bigger than this one that no matter what, we know these aren't going to be pulled off. This one is so much bigger than this one that we know this is a much, much, much weaker acid, and therefore, if this compound is treated with base, the base is going to go for the easiest thing possible. It's going to grab off the most acidic proton, and so it's going to be this one. And so this base will grab off this proton, which is going to give us this as our conjugate base. And then later this year, we're going to see other things that could happen, but just trying to recognize which is the most acidic hydrogen is important. Now, in this example, we have this compound, which has an amine and an alcohol, and we have HCl, hydrochloric acid. So that means this is going to be our acid, and this is going to be our base. But let's be more specific. So these carbons can't act as bases. They don't have a lone pair that could grab a proton, but nitrogen could act as a base. We saw that in an example with methylamine. This oxygen could act as a base. We saw that in an example using methanol. So if we're looking at these two, then we need to decide which one of these is the stronger base. How do we figure out which is a stronger base? We have to focus on their conjugate acids. So if we think about some R group connected to NH3 plus, or if we think about some R group connected to OH2 plus. So the R group is just generic, and let's think about this. So here we're looking at a protonated version of an amine. So after the amine has acted as a base and grabbed off a proton, we have this ammonium ion. Ammonium itself has a pKa of about 9.3, so I think it's safe to assume that an ammonium ion with a carbon group is still going to be somewhere around 9. With an alcohol, we can think about a protonated alcohol, and we saw one on the previous slide, and that had a pKa of about a -2 or a -3. So what we're looking at then would be a conjugate acid with a pKa of 9, or a conjugate acid with a pKa of -2 or -3, and that makes this one the stronger acid, and therefore this is the weaker acid, which means this would be the weaker base, and this one would be the stronger base. So, although we have two potential bases in this molecule, the stronger base is the one that is going to react. And so This base grabs off a proton, and that will give us HO, CH2, CH2, NH3 plus, and Cl minus. Right? So being able to look at a molecule and identify what could be potential acids, what could be potential bases, and then figuring out who's the stronger acid within the molecule, who's the stronger base in the molecule, that is something that's very important to be able to do. So getting practice writing out acid-base reactions, predicting the position of equilibrium, using pKa values to figure out the relative strength of acids, and then the relative strength of bases, that's going to be very important practice to get.